Since we have been able to commercially manufacture plastic on a large scale, so roughly since the 1950s, 8.3 billion metric tons of plastic has been produced by 2015. Of this 8.3 billion, 6.3 billion metric tons becomes waste, so that means only around 9% of plastic ends up recycled. By 2050, roughly 12,000 metric tons of plastic waste will be in landfills or in the natural environment. I can't imagine that plastic encroaching on your space, mine, or any other living things is very appealing, so it makes sense that we need to rethink the plastics that are a part of our everyday lives. One way to do this is by avoiding making a ton of plastic waste in the first place, but how do we do that without getting rid of plastics entirely? Some of the plastics we use are necessary for efficient, lightweight products, so perhaps we need some kind of plastic that disappears when we're done with it. Plastics are comprised of polymers, large molecules that contain repeating units of some chemical structure, otherwise known as a monomer. Many of these were chosen for their inertness and stability, but these qualities can become negative when it comes to how long a product lasts after it no longer becomes usable. Many plastics take hundreds of years to degrade, and some, like styrofoam, can last virtually forever. Even more concerning, plastics often do not degrade into smaller, harmless molecules, but into microplastics instead. These are microscopic, less than 5 mm particles of man-made polymers that are easily spread throughout soil and water. While there is no certainty on the health risks they pose, it is very possible that microplastics can both release and absorb harmful chemicals. Ideally, we would want a plastic that is degradable, sustainable, and leaves no harmful traces behind. Promisingly, there are plastics that are like this: polyhydroxyl alkanoates, PHAs, and polylactic acids, or PLAs. PHAs are a kind of polyester, polymers that contain an oxygen within the carbon backbone of the monomer, such as in poly-R3-hydroxybutane or P3HB here. These polymers are commonly found in nature, often as the product of bacterial fermentation of lipids and/or sugars. P3HB here is produced by microorganisms like Methylobacterium rhodesium in response to the lack of appropriate nutrients or stress. Using natural producers of PHAs or specimens that have recombinant DNA from these natural producers, it becomes feasible to produce bioplastic from various carbon sources. These microorganisms can also digest PHAs into simple, non-toxic metabolites like carbon dioxide and water. This is what affords PHAs a finite, benign life cycle. Similar to PHAs, PLA is a kind of polyester. They are commonly made from fermenting plant-based starches such as sugarcane or corn. As of 2010, PLA is the second most consumed bioplastic in the world, but they still lack an industrial/commodity presence, primarily due to their lack of durability. In order to have feasible commercial presence, bioplastics must be both multi-use and multi-application. However, it is possible to make tougher, more heat-resistant composites by dispersing the appropriate additives throughout PLA. Typically, PLA is synthesized via the direct condensation of lactic acid monomers or with ring-opening reactions with lactic acid and lactide. These processes often require elevated temperatures and/or metal catalysts, therefore alternative methods are considered. Much like PHA, PLA can also be synthesized via microbial means. In 2009, Yu Kyung-jung and associates were able to metabolically engineer E. coli to directly ferment PLA in a copolymer, poly-3-hydroxybutyrate co-lactate, or P3HB co-LA. Prior to this study, reported methods were not very efficient, but Jung's team reports that the engineered strain can produce PLA at 11% weight from glucose and P3HB co-LA with 55 to 86% molar lactate up to 56% weight from glucose and 3HB. With interest in commercial application of PHAs and PLA, it comes as no surprise that there is interest in their application in 3D printing or additive manufacturing. This is often tied to their potential scientific, industrial, or medical application, as many scientific instruments, machine parts, and medical tools/implants have complicated designs on a relatively small scale. Creating molds for such parts can be both time-consuming and difficult. However, additive manufacturing lets you construct highly detailed products with specific functions. The most familiar kind of additive manufacturing is fused deposition modeling, or FDM. Besides the conditions necessary to get the polymer soft enough for extrusion without degradation, The very properties of the polymer will shape the properties of the printed product. One kind of polymer may require a narrow temperature range necessary for proper extrusion, but it yields a soft, flexible structure that does not fracture under pressure. PLA is a possible contender for use in 3D printing, as it can make complex but biodegradable products. However, PLA by itself is brittle, limiting its use in high-performance situations. A means around this issue, then, is to co-extrude the PLA with some other stronger component, such as carbon nanofiber. Carbon nanofiber by itself is quite strong, but it tends to lose its strength when it is chopped up into small rods or powder. A way around this, then, is to extrude PLA with a nanofiber core. While it may have some inherent anisotropic weakness in pulling from the ankle perpendicular from the fiber, this reinforcement greatly boosts its tensile strength compared to pure PLA. Much like PLA, additives can be added to PHA filaments to alter their properties and make them more suitable for different materials. For example, cork powder, a natural product that is viscoelastic, has high impact recovery, and is low density, can be added to a PHA matrix to make it more flexible. PHAs and PLA can be used to develop new technologies with a biologically benign twist. Of particular use is in the medical field in regard to biomedical structures such as implants, sutures, and the like. PLA and PHA filament/powder can be used in the fabrication of artificial tissue or scaffolds for bone regeneration. Besides FDM, PLA and PHAs can be used in selective layer sintering or SLS, wherein polymer particles are fused together with lasers. PLA is actually semi-crystalline, which causes it to change viscosity and density upon melting and crystallization. That means that it can be used to create porous scaffolds for bone tissue reconstruction. PHA alone has also been used to create bone tissue scaffolding, and like PLA, the main draw is its biodegradable aspect. Another use for PHA is in marine panels for crab and lobster traps that end up at the bottom of the ocean after use. These traps continue to work, ensnaring and killing marine life. PHA could potentially be used to create inbuilt escape hatches that arise naturally from degradation after the fishing season is over. Testing the conditions where these panels would exist, such as in water and around different bacteria cultures, requires easily testable prototypes, something FDM can do with ease. The problem, then, is PHA is unable to extrude into a consistent filament. Finding a ways around this is the goal of Richard Thackson's senior project, and he finds that extruding the PHA at a lower temperature, giving more melting time for the PHA pellets in the hopper, and altering the spooler can make the filament more consistent in both composition and diameter. Currently, there is still necessary work to be done when it comes to PLA/PHA application, whether in additive manufacturing or by current industrial models. However, that does not imply that no headway has been made into applying PHA/PLA into commercial settings. One company, Genesis Bioindustries Incorporated, is a Canadian company that converts food waste into PHA filaments. The waste is broken down into volatile fatty acids by bacteria, then are added to another bacteria culture that metabolize the fatty acids into PLA. Next, the PHA is extracted, then purified, with the process taking only about a week to complete. What's more, Genesis intends for their polymer filament to be compatible with most FDM printers, with parameters such as extrusion speed and melt flow rate being process-specific. Furthermore, they hope to scale up the process so that the entire plant can repurpose an entire community's food waste into ready-made PHA pellets. Such innovations or far-reaching predictions of product life cycles may become compulsory for industries as we enter an age of heightened environmental consciousness. The most comprehensive solutions will be found from interdisciplinary efforts, from engineers, from polymer scientists, from environmentalists, industrialists, and more. Thank you for watching, and we will see what the future holds.